9.2 number 20. So there's a lot to this problem. Might as well show you several different ways of doing it. And there's shorter ways and there's longer ways of doing it. So the long way, but the most straightforward, like if you're trying to find the first four terms and general term for this, for f, using it Taylor's series or Taylor polynomial, it's actually Taylor's theorem. We could find f of 0, f prime of 0, f double prime of 0, and so on, and do it using Taylor's theorem. So we'll do it that way. I'll show you an easier way of doing it. Then we have to do the same thing for g. And I'll do it at least a couple ways for g also. Alright, so if f of t is this, then this is all part A here. So f of 0, if I plug in 0, I get 2. Okay, so one initial coefficient is 2. F prime, well, we could find the derivative of that. You end up getting 4t 1 minus t squared to the negative 2. And then f prime of 0 is 0, if I plug in 0. And then we do another derivative. So far I have f of 0 is 2, f prime of 0 is 0, f double prime is equal to 16t squared. I'm not showing you how to do it. I'm actually just reading off my notes to save us time. So assuming that you could find the derivatives, 1 minus t squared to the negative 3 plus 4, 1 minus t squared to the negative 2. And then we do f. So we know that it's centered at 0 because it's always at 0. So f of 0, f prime of 0, f double prime of 0. Looks like it's 4. Do another derivative, f triple prime of 0. Not even showing you that. Looks like it's 0. And the fourth derivative at 0 is 48. Okay, so using the Taylor's theorem, we know that we need four terms. So our first term, f of 0, is 2. So it's 2 x minus 0 to the 0 over 0 factorial. Plus my next initial coefficient is 0, x minus 0 to the first over 1 factorial, plus 4 x minus, so I know it's x minus 0 because it's centered at 0. It's a Maclaurin series, so I mean I wouldn't expect you to write x minus 0 here to the first. So now it's squared over 2 factorial, plus another 0 term, plus so f triple prime is 0, 0. Okay, so fourth prime is 48 x cubed, no, that was cubed, x to the fourth over 4 factorial. So I have 2 plus 0 plus, let's see, 4x squared over 2, so 2x squared plus 4 factorial is 4 times 3 times 2 times 1, so that's 24, so it would be 2x to the fourth. So using this process, we're supposed to first find the first 4 terms. I've only done 3 terms. So I would need probably another 2 derivatives. I'm not very interested in doing that. So you can see what the pattern is. There's your first 3 terms. So the next term is going to be 2x to the 6th. There's our first 4 terms. Alright, so it would be 2 times x to the 2n. So when when n is 0, we get 2. When n is 1, I get 2x squared. When n is 2, I get that. N is 3, I get that. So our general formula would be complete series to represent what f of t is here. Okay, so that's using Taylor's theorem. Another way you could have done it is we know that f of t is equal to 2 over 1 minus t squared. So think of it as 2 times 1 over 1 minus t squared. So here's our initial term over 1 minus our r. So it's this in parentheses is 1, and then we're multiplying by t squared. Our r is t squared, so plus t squared plus t to the 4th plus and so on, t to the 2n, and I still have my 2 out front, so it's 2 times everything. So it's 2 plus 2t squared, I guess their x is up here, now they're t's, plus 2t to the 4th plus 2t to the 2n. Alright, so we have a couple approaches on how to find Taylor series for f of t, which is right here. So that was part A. Part B is doing the same for g. So we could use the Taylor's theorem finding g. So g is the integral 0 to x of f of t dt. Okay, so that's what's given to us. So if we wanted to, we could find g of 0, g prime of 0, g double prime of 0, and so on. Well, g of 0 is, if I plug in 0 for x, I'm integrating function from 0 to 0. So by definition, that is 0. G prime, so the derivative of g, would just be, well, g is the antiderivative of f. So, so if this is g, this is f. G represents the area underneath the curve of f, because g is the integral of f. So if I find the derivative of g, I'm actually just finding f. So g prime of 0 is f of 0, which we already know from the previous part. And part A is 2. G double prime is f, so we're doing another derivative, f prime of 0, which we know is 0. G triple prime is f double prime, which is 4. G fourth derivative is f triple prime of 0, which is 0. G the fifth derivative of 0 is equal to f to the fourth derivative of 0, which is 48. So those are our initial coefficients. So we can say 0 over x to the 0 over 0 factorial plus 2x to the first over 1 factorial plus, pause here. Alright, so where was I? So that plus 0x squared plus 4x cubed over 3 factorial plus 0x to the 4th, and then 48 plus 48x to the 5th over 5 factorial. Okay, so if I clean that up, I'm only going to have 3 terms again, but we'll call that good. So that's 2x, 4 over 6 is 2/3 plus 2/3 x cubed and 48 over, what's that, 120? 48 over, so 24 over 60, 12 over 30, 6 over 15, 2 over 5, 48. Should have just done this initially. Yeah, 2/5 plus 2/5 x to the 5th. There's my first three terms of g of x. If I want an nth term, looks like it's going to be, well, we can figure it out. Looks like there's 2 in all of them, so it's 2 x to the 5th over 5 and so on. So it looks like it's like this would be 2n plus 1 x to the 2n plus 1 over 2n plus 1, and then still have the 2, so it'd be 2 times that. So let's see if that works out. So if x, let's plug in 0 for n, I get 2x to the 1, so 2x over 1, so I get 2x. If I plug in 1 for n, I get x to the, so 2x cubed over 3. How could I have done it differently? Well, we know that f, using our, like a geometric series, infinite geometric series formula, we know that it's initial over 1 minus r. So that's my f. And I know if I just integrate f, I get g. So I can integrate my existing series for f, and I would get, let's see, g would be the antiderivative of that, which would be 2x plus 2, it'd be 2 cubed, so 2 cubed over 3 plus t to the 5th over 5. So we're getting the same thing here. Like, here's my long way, there's my short way, and then the nth term, if we integrated this, it'd be t to the 2n plus 1 over 2n plus 1, and then I have a 2 there. So plus a bunch of terms. So I have, again, this is x's and those are t's, but we get the same answer. So there's my g, using like step-by-step integration or using the Taylor's theorem to do it. There's one last way of doing it I have written down in my notes. I'm not going to show you, like, I'll just show you what I did on here. So if you notice that if you integrated, like, we're trying to find what the integral of this is, integral of f. We're trying to generate what g is. So you could find the antiderivative. To find the antiderivative of that, you'd have to use partial fractions. So we do some partial fractions, rewrite it using partial fractions, and we get this. So you get natural log of 1 plus x plus natural log, that's actually minus because of the negative c, minus natural log of 1 minus x. Okay, and we know, so off of our like Maclaurin series, we know that the natural log of 1 plus x is this, and the natural log of 1 minus x is this, and we're subtracting them. So you'd end up with x minus a negative x, which is 2x. We have negative x squared over 2 minus a negative x, so that's 2 of them. So you end up, so a negative, actually plus the same, they disappear. We get x cubed over 3 minus a negative x cubed, so that's 2x cubed over 3. So every other term disappears, every other term combines, and you end up getting the same answer. There is a third way to generate g of x. Alright, I think that's enough on that problem.